time itself might not have always existed. The Big Bang is often called the beginning of everything. But what if it was not the true start? This journey into the physics of pre-existence will challenge your understanding of reality itself. You will explore ideas like quantum fluctuations, multiverse theories, and the possibility of a timeless state before our universe began. We will investigate what might have been happening before time as we know it, and how something could emerge from what we call nothing. By the end, you will see the cosmos in a completely new way, with insights that stretch the limits of science and imagination. How do you picture nothingness? Our everyday experience of time is so intuitive it feels absolute. We watch the sun rise and set. We feel ourselves grow older. We remember the past and anticipate the future. But physics reveals this is merely a shadow of a much deeper reality. Time, in its most fundamental form, is not a universal metronome ticking at the same rate for everyone everywhere. Instead, it is a flexible dimension, woven together with the three dimensions of space into a single fabric called spacetime. This is the revolutionary insight from Einstein's theory of relativity. A clock ticks slower near a massive object like a planet, and for an astronaut traveling at a significant fraction of the speed of light, time literally passes more slowly than it does for those of us left on Earth. This means time is not separate from the universe. It is a property of it, shaped by matter and energy. This fabric of spacetime allows for the very concept of cause and effect. For one event to influence another, they must be connected within this continuum. There is also a powerful directionality to time in our universe, an arrow that flies relentlessly from the past toward the future. This is deeply tied to a concept known as entropy, which is essentially the measure of disorder in a system. The universe consistently moves from a state of lower entropy or more order to higher entropy or more disorder. Think of an ice cube melting in a glass of warm water. It moves from a structured, ordered state to a chaotic, mixed one, and this process is irreversible. This constant increase in entropy gives our experience of time its undeniable forward direction, but this understanding creates a monumental puzzle. If time is a dimension that can be warped and stretched, and if it is an integral part of our universe, what happens if we rewind the cosmic film all the way back to the very beginning, to the Big Bang? The equations of general relativity suggest that at that point, the density and temperature become infinite, and the fabric of spacetime itself curves into a singularity, a point where our laws of physics simply break down. This implies that time, as we know and define it, might have had a definitive starting point, so we are left with a truly baffling question. If time began with the universe, how can we even speak of a before? What does it mean for something to precede time itself? To venture into that realm, we must contemplate the possibility of a state with no time at all, a frozen eternity where the words before and after hold no meaning. This singularity is not a place or a moment in time we can describe. It is the edge of the map, a warning that our understanding has reached its limit. For decades, we have spoken of the Big Bang as the absolute beginning, the moment everything started from a single point. But what if that interpretation is incomplete, a story told with the first few pages of the book forever missing? The equations of general relativity point to this singularity, a state of infinite density and temperature where the rules of space and time cease to function. A physicist cannot work with infinity in their calculations. It is a sign that the theory itself has failed. This breakdown is not an end but a clue. It strongly suggests that the Big Bang was not a true beginning from nothing, but rather a dramatic transformation from some other state of existence that we do not yet understand. It marks a boundary beyond which our current physics cannot see, implying that something must have preceded it. Cosmologists now explore the compelling idea that the Big Bang was a phase transition, a cosmic shift analogous to water freezing into ice. Our universe, in this view, might have crystallized out of a prior, exotic form of reality. This could have been a contracting universe that collapsed and then rebounded in a great bounce, or perhaps it emerged from a seething, chaotic quantum foam where the very concepts of before and after are meaningless. This shifts our entire perspective. We are no longer looking for a single, explosive starting pistol, but rather a single event in a much longer and more complex process, possibly a cyclical or emergent one. This opens the door to profound theories about what existed before and how our familiar cosmos came to be, suggesting our entire history might be just one chapter in a far grander story. To venture beyond the singularity, we must turn to the bizarre and counterintuitive rules that govern the smallest scales of existence, the world of quantum mechanics. This is a realm where the very idea of a vacuum, of empty space, is completely redefined. In our everyday experience, nothing means a complete and total absence of anything. But in quantum physics, what we call empty space is not empty at all. It is a seething, bubbling cauldron of potentiality, alive with fleeting energy. This is due to a fundamental rule of the quantum world known as the Heisenberg uncertainty principle. In simple terms, this principle states that for extremely short periods of time, energy can appear out of nowhere, borrowing from the future before vanishing again, as long as it pays back the debt quickly enough. This leads to a stunning phenomenon where pairs of particles and their antiparticles spontaneously wink into existence, exist for an unimaginably brief moment, and then annihilate each other, returning the borrowed energy to the vacuum. They are called virtual particles, and they are a proven fact of our universe, observed in laboratories. So the quantum vacuum is not a true nothingness. It is a something, a field of immense latent energy constantly giving birth to fleeting particles. This ongoing dance of creation and destruction is a quantum fluctuation. Now, consider the implications of this. If the vacuum can spontaneously generate pairs of particles, could it, under the right conditions, generate something far grander? Could an entire universe be the ultimate quantum fluctuation? This is not just a wild guess, it is a serious cosmological theory. The idea is that our entire cosmos could have begun as a tiny, random bubble of energy, a fluctuation in some primordial, timeless void. This tiny bubble, filled with a tremendous amount of potential energy, then underwent a period of hyper-fast expansion known as inflation, stretching from a subatomic speck to a macroscopic universe in a fraction of a second. This inflationary burst would have provided the initial push, the seed from which all galaxies, stars, and planets would eventually grow. In this view, the Big Bang was not the beginning of everything, but rather the moment this infant universe heated up and began its evolutionary journey. This theory profoundly challenges our deepest intuitions about cause and effect. It suggests that the universe did not need a cause in the traditional sense, that it could simply be a random, statistical event, one possible outcome in an eternal, quantum sea of possibilities. It implies our entire reality might be one random roll of the cosmic dice. But if our universe is just one possible fluctuation, what about all the others? This quantum sea of possibilities leads us to an even more staggering idea. If a vacuum can spawn one universe, what is to stop it from spawning an infinite number of them? The theory of eternal inflation paints a picture of a multiverse, a boundless cosmic ocean where new universes are constantly bubbling into existence, each one a separate pocket of reality with its own unique properties. In this grand view, what we call the Big Bang was not the beginning of everything, but merely the moment our own local universe inflated and cooled into being. Before our time began, this metacosmic process was already underway. An endless number of other universes could have been born, lived out their cosmic histories, and perhaps even died, all in a framework where time itself is relative. Our arrow of time, our beginning, is just a local event, a single thread in an infinite and eternal tapestry. This suggests that pre-existence is not a single, static state of nothingness, but a dynamic, endless process of creation. The vacuum before our time was not empty, it was fertile, endlessly giving birth to new realities, each with its own physics, its own dimensions, and its own definition of time. Some of these universes might be stillborn, collapsing instantly, while others might be vast and stable enough to spawn galaxies and life. Our universe is not special, it is simply one that worked, one where the conditions were just right for us to emerge and ask these very questions. So when we ask what was happening before our time began, the answer might be that everything was happening, an infinite number of times over, in a meta-reality that has no beginning and no end. But these are not the only visions of a timeless origin. Another profound idea comes from the world of string theory, a candidate for a theory of everything. This framework proposes that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating strings. Their different vibrations give rise to all the particles and forces we observe. But for the math of string theory to work, it requires more than the three spatial dimensions and one time dimension we experience. It demands extra dimensions, curled up into a space so small we cannot perceive them. Within this rich theoretical landscape, a compelling model called the pre-Big Bang scenario emerges. It suggests our universe was born from a cataclysmic collision. The actors in this drama are not particles, but structures called branes, short for membranes. These are multidimensional objects that could exist within a higher dimensional void, a true bulk space. Our entire universe, with all its three dimensions of space and one of time, might be confined to just one of these three-dimensional branes. Before what we call time, this brane and another could have been drifting or oscillating in this timeless, higher dimensional expanse. Their motion might have been slow and gradual for an eternity we cannot measure, until finally they drew too close. The collision between these two colossal branes would have been an event of unimaginable energy, flooding both with heat and radiation. This violent interaction, this cosmic clash in a realm beyond our perception, could have been the true spark that ignited our Big Bang. In this view, the singularity is not a beginning but an aftermath, a moment of intense energy release from a collision that happened in a state beyond our conventional understanding of time. This model elegantly sidesteps the problem of the infinite singularity, offering a mathematically sound picture of a pre-temporal state. It suggests the origins of everything we know lie in the silent, dynamic dance of entities in a reality with more dimensions than we can possibly conceive, a hidden geometric ballet whose final movement gave birth to our entire cosmic story. Another radical idea completely reimagines the birth of our cosmos, turning the Big Bang into something else entirely. Loop quantum gravity, a rival to string theory, proposes that the universe did not begin from a singularity. Instead, it underwent a great bounce. In this view, the Big Bang was not a beginning but a turning point, a moment of cosmic rebirth. The theory suggests that before our expanding universe came into being, there was a previous phase where the cosmos was contracting, collapsing in on itself under the immense pull of gravity. As this earlier universe compressed, it reached a point of incredible density. But unlike in classical physics, where this collapse would continue into an infinitely dense singularity, the quantum properties of spacetime itself put on the brakes. Imagine squeezing a spring with all your might. There is a point where you cannot compress it any further, and it pushes back with tremendous force. In loop quantum gravity, spacetime is granular, made of tiny, indivisible loops. This granularity prevents the universe from reaching a true point of infinite density. Instead, these quantum effects generate a powerful repulsive force, causing the collapsing universe to rebound, to bounce, and explode outward in a new phase of expansion. This event is the Big Bang we observe, not a beginning from nothing, but a transformation from a previous state. This leads to a mind-bending possibility about time itself. In that previous contracting phase, the arrow of time might have been reversed relative to our own. From the perspective of that dying universe, time would have been flowing towards the bounce, the moment of its own death, which from our side looks like our birth. This creates a cyclical model of existence, an endless sequence of universes expanding, contracting, and bouncing back again in an eternal cycle with no definitive start or finish. The question of what happened before time began loses its meaning because there may have always been a before, an infinite series of cosmic cycles stretching back forever. This challenges the very idea of pre-existence as a single, static state of nothingness, replacing it with an endless, dynamic process of death and rebirth. Each of these theories, from quantum foam to colliding branes, points toward a reality where time is not the absolute ruler we perceive it to be. This leads us to a truly radical possibility, that time itself is not a fundamental feature of the cosmos but an emergent property, a side effect of something deeper. At the most extreme scales, like the unimaginably small Planck scale, the smooth fabric of spacetime might dissolve into a grainy quantum foam. In this primordial state, the very concept of time loses all meaning. There is no before or after, no past or future. Instead, everything simply is, frozen in a single, eternal now. This is not a state of inactivity, but one of pure potential, where every possible configuration of the universe exists simultaneously. How could such a frozen realm give rise to the flowing time we experience? Think of it like a single, perfectly still frame from a movie. By itself, it is timeless. But when you connect it to other frames, a sequence emerges, and with that sequence comes the illusion of movement, of time passing. In a similar way, our experience of time may emerge from the complex correlations and relationships between countless quantum events. A key equation in quantum cosmology, the Wheeler-DeWitt Equation, famously describes a universe without time. It paints a picture of the entire cosmos as a static object, a frozen block where the Big Bang and the distant future are equally real and present. In this view, the moment before time began was not an event but a state of being. The universe was a vast landscape of pure mathematics, a realm of every possible reality waiting to be actualized. Our arrow of time, our history, is just one path through this infinite landscape, one story read from this timeless book. The Big Bang, then, was not a beginning in time, but the moment this timeless potential unfroze, when correlations between quantum particles locked into place and created the consistent, flowing sequence we now call causality. We are not moving through time, time is moving through us, an emergent property of a deeper, timeless reality. This profound mystery brings us to a fundamental force that shapes our reality, the relentless drive of entropy. Entropy is essentially the universe's measure of disorder, and its constant increase is what gives time its undeniable forward direction, its arrow. We witness this everywhere, from a melted ice cube that never spontaneously refreezes to a shattered vase that cannot reassemble itself. The universe consistently moves from order to disorder, and this process is irreversible. But this creates a baffling paradox at the very beginning. If the universe is always becoming more disordered, then rewinding the cosmic film means it must have started in a state of incredibly low entropy, a condition of exquisite and highly improbable order. What could possibly have set this initial state, this pristine cosmic spring that has been unwinding ever since? Some physicists propose a radical answer rooted in the very nature of pre-existence. They suggest that before our Big Bang, there was not a void of true nothingness, but a chaotic, timeless soup where entropy was already at its maximum. In this state of ultimate disorder, every possible configuration of particles was equally likely, a form of bland, featureless equilibrium. Within this eternal chaos, a rare and colossal statistical fluctuation could have occurred. Imagine a vast ocean in a perfect, motionless calm. Suddenly, and entirely by chance, a single, massive wave rises up before settling back down. In a similar way, a random fluctuation in this maximum entropy state could have briefly created a pocket of stunningly low entropy, a bubble of incredible order. This bubble, this rare statistical anomaly, became our universe. The moment of this fluctuation was the true beginning, the point at which the arrow of time was notched and set into motion. It means our entire cosmos, with all its galaxies, stars, and conscious life, might be the result of a fleeting and fantastically unlikely event, a temporary eddy of order in an endless, churning sea of disorder. Our existence is not just a product of time, but a fascinating anomaly against a backdrop of entropic eternity. This dormant state is known as a false vacuum, a condition of profound but unstable equilibrium. Picture a marble resting precariously at the very peak of a perfectly symmetrical hill. It is in a state of high energy, and while it appears stable for a moment, this situation is utterly unsustainable. The slightest nudge, the tiniest perturbation, will send it rolling down into the valley below, releasing its pent-up energy. The inflattened field before time is theorized to be that marble, frozen at the top of its hill. The universe was not empty, it was brimming with potential energy, locked in a timeless, motionless state of suspended animation. There were no events, no dynamics, no flow of time as we know it, only this perfect, unstable symmetry. So what provided the nudge? In the absolute quiet of this pre-existence, the only possible catalyst is the random, unpredictable jitter of quantum mechanics. Through a process called quantum tunneling, the inflattened field could have spontaneously made the transition, like the marble suddenly appearing in the valley without ever rolling down the hill. This bizarre quantum effect allowed the universe to bypass the energy barrier, triggering a catastrophic release of the inflattened field's stored energy. This release did not create matter and energy from nothing. It converted the immense latent energy of the false vacuum into the hot, dense plasma of the primordial universe. This event was the ignition of inflation, a period of hyper-fast expansion that smoothed and flattened the cosmos, setting the stage for everything to come. The Big Bang, then, was not the very first moment, but the moment this inflationary expansion ended, the moment that energy decayed and reheated the universe into the fiery beginning we now study. This means the true genesis was a quantum event, a random fluctuation in a timeless, energy-rich void, a single note struck in the silence that sparked the symphony of our cosmos. These scientific theories force us to confront a paradox that has troubled philosophers for centuries. If our concept of time truly began with the universe, then the word before becomes meaningless when applied to its own origin. How can something precede the very framework that allows precedents to exist? This is not just a puzzle of physics, but a profound philosophical challenge to our most basic understanding of reality. The great thinker Immanuel Kant argued that time is not something we discover in the world, but a fundamental structure of the human mind itself, a necessary lens through which we perceive everything. It is like trying to see the outside of your own eyeballs, an impossibility built into the very act of seeing. If Kant was right, then the notion of a state before time might be a logical contradiction, a question that can be asked with words but can never truly be answered, because it tries to step outside the boundaries of human thought. Martin Heidegger approached the problem differently, diving into the nature of being itself. He suggested that time is the very horizon of being, the context in which existence unfolds and has meaning. To ask what was before time, in this view, is to ask about a mode of being that is completely alien to our own, a form of existence so different we may have no capacity to comprehend it. This shifts the entire quest. We are no longer just searching for a physical description of a pre-temporal state, but grappling with the limits of our own consciousness. Can a mind that evolved within time ever truly grasp the concept of timelessness? Our language, our logic, and our intuition are all built upon the assumption of cause and effect, of before and after. They might be utterly useless tools for describing a reality where those concepts do not apply. This humbling realization enriches the scientific pursuit, framing it within a much larger human endeavor to understand our place in the cosmos. Some truths may forever reside beyond the reach of empirical proof, in the realm of metaphysical speculation, where science and philosophy meet to ponder the ultimate mysteries of existence. This quantum foam is the ultimate example of something from nothing. According to quantum field theory, the vacuum of space is not a barren void but a dynamic, energetic medium, a seething ocean of potential. Even in its ground state, what we would call its empty state, it is alive with activity. This is due to the fundamental uncertainty inherent in the quantum world, where energy can borrow from nothingness for fleeting instants, allowing pairs of virtual particles to spontaneously pop into existence and vanish again. This constant, frantic dance of creation and annihilation is the vacuum fluctuation, and it gives the void a kind of energy, a latent power waiting to be unlocked. Now project this concept backward to the state we might call pre-existence. Before our universe and its arrow of time began, this vacuum energy could have existed in a timeless, fluctuating state. Without the flow of time to sequence events, every possible quantum fluctuation would simply be a vast and eternal foam of potentiality. In this view, pre-existence is not a sterile nothingness but a fertile ground of infinite possibilities, a landscape where the laws of physics as we know them are not yet fixed. Reality here is not deterministic but profoundly probabilistic. Every possible configuration of a universe, with every possible set of physical constants and dimensions, exists as a potential waiting to be realized. This offers a powerful scientific basis for how something can emerge from what we perceive as nothing. The energy for the birth of a universe is not created from nothing. It is converted from the immense latent energy of this primordial vacuum. The conservation of energy, a fundamental law within our universe, may not apply to the meta-reality that gave it birth. Our entire cosmos could be the result of one particularly large and stable quantum fluctuation in this eternal foam, a bubble of space-time that inflated and cooled into the reality we now inhabit. We are not a violation of physical law, but a magnificent expression of quantum potential made real. This leads us to a final, breathtaking possibility, that reality itself is a projection, a cosmic illusion. The holographic principle turns our understanding of the universe inside out. It suggests that all the information contained within any three-dimensional volume of space, all the stars, planets, and people, can be perfectly encoded on its two-dimensional boundary, like the data on a holographic film. A black hole presents a profound puzzle for physics, as it seems to destroy information that falls into it, which the laws of quantum mechanics say is impossible. The holographic principle emerged as a stunning solution. It proposes that all the information about what falls into a black hole is not lost, but is instead smeared and stored on its event horizon, its two-dimensional surface. The three-dimensional interior is, in a sense, just a manifestation of that information. Now, apply this radical logic to the origin of everything. What if our entire universe, in all its four-dimensional glory, is the projection of information stored on a lower-dimensional surface at its boundary? This flips the script on pre-existence entirely. Before time and space as we know them, the universe may not have been a place at all, but a vast, timeless sea of pure information, a cosmic code. The fundamental building blocks of reality would not be particles or strings, but bits, like the ones and zeros in a computer. In this view, the moment of the Big Bang was not an explosion in a void, but the instant this primordial information began to be processed, computed, and projected. Time itself could be an emergent property of this computation, a side effect of information being processed. The arrow of time might simply be the direction in which this cosmic calculation runs. We are not living in a universe of things, but within a universe of data, a magnificent hologram whose source code was written in a state of timeless, lower-dimensional potential. Our reality is the redoubt. Another profound vision dissolves the need for a beginning entirely. Stephen Hawking and James Hartle presented a beautifully elegant idea called the no-boundary proposal. They asked a simple but revolutionary question: what if the universe is completely self-contained with no boundary and no edge, much like the surface of the Earth? You can travel across the Earth forever without ever falling off an edge because it is a closed surface. Hawking and Hartle applied this same logic to the entire cosmos, but they blended time with space to do it. In their model, when you rewind the clock all the way back to what we call the beginning, time itself smoothly transforms into a dimension that behaves more like space. Think of the North Pole on a globe. If you ask what is north of the North Pole, the question has no meaning. It is not a point in space you can go beyond. It is the boundary of your coordinate system. In the same way, the Big Bang is not a moment in time you can look before. It is the ultimate North Pole of time. There is no before, because before implies a time that came earlier, and in this model, time as we know it did not exist in that state. The universe simply is a finite but unbounded whole. This vision was achieved using a mathematical approach called Euclidean quantum gravity, which treats time as an imaginary dimension to allow for this smooth geometric transition. The primordial universe is not a point of infinite density, but a tiny, slightly curved, four-dimensional shape without any sharp edges or singularities. It is a perfectly smooth origin story that requires no creator, no prior universe, and no mysterious pre-existence. The cosmos just seamlessly comes into being as a finite, closed entity, and our entire history unfolds from that smooth geometric genesis. The question of what happened before the beginning is rendered obsolete, a linguistic trap built from our limited intuition about time. In this view, the universe was never born, it just is. This deep connection between time and reality leads us to a startling frontier, the role of the mind itself. Some interpretations of quantum mechanics present a universe that is fundamentally probabilistic, a realm of potentialities where particles exist in a blur of all possible states until the moment they are observed. It is the act of measurement, of observation, that seems to force a single, definite outcome into existence. This has led to a profound and controversial idea that consciousness itself might be the catalyst that crystallizes reality from a sea of quantum possibility. If this is true, then what does it say about time? Time, as a sequence of definite events, might be inextricably linked to the presence of an observer. The flow from past to present to future could be more than just a physical process. It could be a cognitive one, a story woven by a conscious mind engaging with the cosmos. This idea is taken even further by the participatory universe principle, which suggests that observers are not passive witnesses but essential participants in bringing the universe into being. We are not just living in the universe is living through us, requiring our observation to become concrete and real. This radically reframes the question of pre-existence. Before our universe and its arrow of time began, there would have been no observers, no conscious minds to separate the potential from the actual. Pre-existence, in this view, would be a state of pure potential, a timeless fog of unrealized possibilities waiting for a mind to give it form and sequence. It implies that time did not just emerge with the physics of the Big Bang, but with the dawn of the first conscious awareness that could perceive its passing. This bridges the cold equations of physics with the inner world of psychology, hinting that our most personal experience of time's flow might be the very thing that gives the cosmos its solidity. Could it be that without a witness, the universe remains a silent, frozen symphony, and that time itself is the music only we can hear? Yet another vision of our cosmic origin emerges from the silent, higher dimensional expanse. The Ekpyrotic universe model presents a dramatic creation story, one where our entire reality is born from a cataclysmic collision. This scenario, deeply rooted in the mathematics of string theory, reimagines the pre-temporal state not as a quantum foam or a singularity, but as a vast, calm, and multidimensional landscape. Within this hidden reality exist structures called branes, which are like immense floating membranes. Our entire universe, with its 3 dimensions of space and 1 of time, might be confined to just one of these 3-dimensional branes. Before what we call time, this brane and another like it could have been perfectly parallel to each other, adrift in a higher dimensional void. They were not moving, not interacting, but simply existing in a state of timeless stasis, like 2 sheets of glass suspended in a perfectly still vacuum. This was a profound and eternal calm, a pre-existence of pure geometry. Then something disturbed this perfect peace. Perhaps it was a subtle gravitational pull or a random quantum nudge in the higher dimensions. The 2 branes began to move, drawn slowly toward one another in a cosmic dance whose final movement would be one of unimaginable violence. Their collision was not a simple bump. It was an event of extraordinary energy release, a clash of entire worlds that flooded both branes with an intense fire of radiation and matter. This violent interaction, this cosmic accident in a realm beyond our perception, is what we now call the Big Bang. It was not an explosion from a point, but a fiery awakening across an entire plane of existence. This model offers a compelling and testable alternative to cosmic inflation. If true, the specific gravitational waves generated by such a colossal brane collision could, in theory, leave a faint imprint on the cosmic microwave background, a relic from the universe's earliest light. Future observatories might one day detect this signature, offering us a glimpse not of a singularity, but of the moment our universe was struck into being, a permanent scar from a collision in the silent dark before time. This logical impasse forces us to question the very foundation of our reasoning. We are hardwired to see the world in chains of cause and effect, a domino rally where each event is knocked over by the one before it. But what if that domino rally only began with the first domino? The idea that the universe must have a cause is so deeply ingrained in us that it feels like a law of nature itself. Yet, if time itself began with the universe, then the principle of causality, which requires time to function, simply cannot apply to the universe's own origin. To ask for a cause of the Big Bang is like asking what is north of the North Pole. The framework for the question collapses. This has led physicists to explore truly mind-bending possibilities like a causal creation. In this view, the universe did not need a cause. It could simply be a brute fact of existence that requires no prior explanation, much like a mathematical truth. Another radical idea is self-causation, where the universe creates itself in a closed, time-like loop, a concept that twists logic into a Möbius strip of existence. At the quantum level, we already see hints that our classical intuition is flawed. Particles can become entangled, instantaneously influencing each other across vast distances in a way that seems to defy the speed of light and any simple notion of cause preceding effect. This suggests that causality, as we understand it, might not be a fundamental rule of reality, but rather an emergent property that crystallized along with time. Before our cosmic clock started ticking, pre-existence might have operated under a completely different set of logical rules, a realm where events are not sequenced but correlated, where reality is a vast, timeless web of connection without a clear before or after. The search for a first cause may be a beautiful but ultimately human error, a projection of our temporal minds onto a timeless reality. These dizzying paradoxes of cause and effect lead us to a vision of reality that is both austere and breathtakingly vast. A compelling hypothesis from physicist Max Tegmark proposes that the ultimate foundation of everything is not energy, not strings, but mathematics itself. In this view, the universe is not described by math, it is math. Our physical reality is just one particular mathematical structure that has somehow become manifest, one specific equation with a solution that plays out as stars, planets, and people. But if this is true, then the concept of a beginning becomes deeply blurred. Mathematical truths do not exist in time. The Pythagorean theorem is not created or destroyed, it simply is an eternal verity. Tegmark's radical idea extends this to all possible mathematical structures. Every conceivable universe that can be described by a consistent set of mathematical rules does, in fact, exist in a vast and timeless multiverse of pure abstraction. This is a modern take on Plato's realm of perfect forms, a domain of ideal shapes and relationships that exists outside of space and time. So what then was happening before our time began? According to this hypothesis, nothing needed to happen. Our universe, along with an infinite variety of others, has always existed in a mathematical sense. There was no moment of creation, only an eternal, silent landscape of logical possibility. Our Big Bang was not a beginning from nothing, but the moment this particular mathematical structure gained physicality, perhaps through a process like symmetry breaking, where a perfect, abstract symmetry fractured to create the rich, complex, and tangible world we experience. In this view, pre-existence is the ultimate reality, a timeless domain of numbers and equations, and our flowing, temporal universe is merely a shadow it casts, a single stanza in an infinite, eternal poem of pure logic. This endless cycle of cosmic death and rebirth presents a profoundly different vision of pre-existence. There was no absolute beginning, no moment of creation from nothing. Before our universe expanded into being, there was a previous cosmos contracting toward its own end, a great collapse known as the Big Crunch, and before that, another universe expanding, and before that, another collapse in an infinite and eternal loop. Each cycle begins with a big bang, but this is not a true beginning. It is a bounce, a moment of cosmic rebound. Imagine a celestial heartbeat, with the universe expanding like a single breath out and contracting like a breath in, over and over again for all eternity. In this view, the state before our time was simply the final, fading moments of a previous cosmic era, a universe growing ever denser and hotter as it hurtled toward its own compression. Time itself, in each individual cycle, has a clear arrow and a clear beginning, but the overarching meta-cycle is timeless, an endless repetition without start or finish. Certain formulations within string theory support this idea, suggesting the physics allows for these grand transitions, these cosmic resets. This offers a kind of comforting symmetry, a universe that is forever renewing itself. But it also raises a deeply puzzling question. If the universe collapses into a singularity and bounces back, what happens to all the information it contained? Every star, every planet, every thought, every memory, is that information utterly annihilated in the fiery crunch, or is it somehow preserved, encoded into the fabric of reality to perhaps reappear in some distorted form in the next cycle? The answer could determine whether each new universe is a truly fresh start or merely an echo of all that came before, an eternal recurrence where every possibility plays out again and again forever. This possibility pushes the question of origin into a realm of pure information. The simulation hypothesis offers a radical answer, suggesting that before our time began, there was only code. Our entire universe, with its galaxies, forces, and laws of physics, might not be fundamental reality, but an incredibly sophisticated simulation running on a computer of unimaginable power in a realm outside our own. In this view, what we experience as the Big Bang was not a physical explosion, but the boot-up sequence of the program, the moment the simulation's initial conditions were loaded and the clock started ticking. The programmers, or the underlying computational system that built our reality, would exist in a meta-time, a framework of cause and effect completely separate from the time we experience within the simulation. For them, our entire cosmic history, from the first nanosecond to the last dying star, could be a completed calculation, a saved file they can review from beginning to end. This means the state before our time was not a void or a quantum foam, but a state of pure potential, a universe in its pre-compiled form, existing as algorithms and data waiting to be executed. Our arrow of time, the relentless flow from past to future, would simply be a variable set by the simulation's parameters, a necessary feature to make the experience coherent for us, the processes running within it. This idea, while entirely speculative and far beyond any current means of testing, forces a profound philosophical shift. It challenges us to see reality not as a given, but as a constructed experience, and it reframes the mystery of pre-existence into the ultimate question of source code. What was written in the program before the run command was issued? But this relentless expansion is not just a detail. It is the central feature of our cosmic era, and its engine is the most mysterious substance in the universe, dark energy. This enigmatic force, which makes up the vast majority of the cosmos, is pushing galaxies apart at an ever-increasing rate, and its nature might be the most important clue we have to the universe's origin story. What if dark energy is not a new player on the cosmic stage, but a ghost from a time before time? Some compelling theories propose that dark energy is actually a remnant, a leftover echo from the pre-Big Bang state. It could be the faint, lingering presence of the very inflattened field that powered the universe's hyper-fast inflationary burst at its birth. Like a cosmic fossil, this energy has been dormant for billions of years, only reawakening recently in cosmic terms to once again dominate the expansion of everything. Or perhaps it is something even more profound, a direct manifestation of the vacuum energy from that timeless, primordial state. In this view, the seething quantum foam of pre-existence did not just create our universe, it imbued the very fabric of space with a latent energy that is now making its presence known. This creates a breathtaking and deeply poetic connection between the ultimate fate of the cosmos and its absolute origins. The force that is determining how our universe will end, whether in a cold, empty fade or a dramatic tear, might be a direct imprint of the conditions that existed before it even began. By studying dark energy and the accelerating expansion it drives, we are not just looking forward into the distant future, we are also peering backward through the veil of the Big Bang, catching a faint glimpse of the timeless reality that gave birth to our own. This fine-tuning of our universe is so precise it defies belief. The strength of gravity, the mass of an electron, the exact value of the cosmological constant. If any of these fundamental constants were altered by even a minuscule fraction, the cosmos as we know it would not exist. There would be no stars, no planets, no chemistry, and certainly no observers to wonder about it all. This astonishing precision leads us to a profound and deeply controversial idea known as the Anthropic Principle. In its simplest form, it states that the universe must be compatible with the conscious life that observes it, because if it were not, we would not be here to notice. It seems like a tautology, a circular argument, but its implications for the pre-temporal state are staggering. If our universe is just one among a vast multiverse, an infinite ensemble of realities, each with its own random set of physical laws, then it is no surprise we find ourselves in one of the rare habitable ones. We are the winners of a cosmic lottery we never knew we entered, but this principle can be pushed further into a more provocative and teleological territory. It suggests that the conditions of pre-existence itself might have been filtered or fine-tuned in some way to inevitably give rise to a life-permitting cosmos. The primordial quantum foam, the colliding branes, the eternal cycle of bounces, perhaps these processes are not entirely random. Perhaps there is a deep principle at work, a bias in the machinery of reality that favors the emergence of complexity and consciousness. This is not necessarily a divine argument, though it can be interpreted that way. It could be a fundamental feature of the mathematical structure of existence, that universes capable of observing themselves are somehow more likely to be realized. It merges the cold, random chance of quantum mechanics with an almost philosophical purpose, implying that the silent darkness before time was not just a chaotic jumble, but a state pregnant with potential, inherently leaning toward the eventual awakening of mind. The question shifts from how something came from nothing to why the something that emerged is so perfectly arranged for us to be within it. This paradox forces us to confront the origin of information itself. If the universe truly began from a singularity, a point of infinite density, then all the information that would ever exist, every star, every planet, every law of physics, should have been crushed out of existence. Yet here we are in a complex, information-rich cosmos. The black hole information paradox offers a profound clue. Physics tells us that information cannot be destroyed. If you burn a book, the information in its words is not truly gone. It is just transformed into smoke and heat, scrambled into a form that is incredibly difficult, but not impossible to decode. Now apply this to a black hole. When something falls in, it seems to vanish forever, its information locked behind an event horizon from which nothing can escape. But Stephen Hawking showed that black holes slowly evaporate, radiating away their mass until they potentially vanish entirely. This creates a crisis. If the black hole disappears, what happens to all that information it swallowed? The leading solution, born from string theory, is that the information is not lost. It is preserved, encoded on the two-dimensional surface of the black hole's event horizon, like a cosmic hologram. The three-dimensional interior is just a projection of that data. This suggests a radical idea for the origin of everything. Perhaps our entire universe operates on the same principle. The Big Bang might not have been the creation of information, but the moment a vast amount of pre-existing information was projected into the three-dimensional reality we experience. So where did that initial data come from? The answer might lie in the strange world of quantum entanglement. When two particles become entangled, they share a connection that defies space and time. They instantly influence each other regardless of distance, as if they are part of a single, unified system. This connection is pure information, a correlation that exists without being tied to a specific location or moment. Now scale this idea up to a cosmic level. What if the primordial state before the Big Bang was not a void, but a vast, timeless web of quantum information, a substrate of entangled relationships? In this view, the universe did not emerge from a random fluctuation of energy, but from a fluctuation of information. The initial conditions, the laws of physics, the constants of nature, were not set by chance, but were the first bits of data to be processed, the starting variables in a cosmic computation. Pre-existence becomes an informational plane, a silent, abstract realm where reality is defined not by things, but by bits and qubits, the ones and zeros of existence. The Big Bang was the moment this data was executed, when the program began to run and the projection of spacetime first flickered to life, rendering the code into the rich, physical world we now call home. This quantum vacuum is what physicists truly mean by nothing. It is not an empty stage waiting for actors, but a vibrant field of activity, humming with impermanent energy. Before our universe began, this might have been the default state of reality, a timeless sea of quantum potential. Within this void, the laws of physics as we know them did not yet apply, meaning the concepts of cause and effect were not yet enforced. This allows for a universe to simply happen, to emerge not from a divine act or a violation of physical law, but as a natural statistical outcome. The universe, in this view, is the ultimate free lunch, a fluctuation that borrowed energy from the gravitational field, which has a peculiar property: its energy can sum to zero. So the positive energy locked in all the stars and planets is perfectly balanced by the negative energy of gravity, meaning the total energy of the cosmos could be zero. This means something could indeed come from nothing, because that nothing was always secretly something, a roiling cauldron of possibility. This redefines creation itself, shifting it from a singular event to a probable process. Our entire existence might be a magnificent accident, a stable bubble that formed in an eternal and unstable void, a single note of order in a timeless symphony of chaos. This profound equation, named for physicists John Wheeler and Bryce-DeWitt, is perhaps one of the most humbling and baffling results in all of theoretical physics. It attempts to do the seemingly impossible, to merge the rules of the very small, quantum mechanics, with the rules of the very large, general relativity. And in doing so, it produces a stunning conclusion, a universe frozen in an eternal present. The Wheeler-DeWitt equation describes the entire cosmos not as a dynamic, evolving entity, but as a single, static object. Time, the variable t that flows through every other equation in physics, simply vanishes from this master formula. It is not a factor. The equation suggests that at the most fundamental level, the universe does not happen, it simply is. This is the ultimate block universe theory, where the Big Bang, our present moment, and the heat death of the cosmos 10 trillion years from now all exist simultaneously, like points fixed on a vast, unmoving tapestry. Before our experience of time began, the universe would have been in a state of pure potential, a superposition of every possible configuration it could take. Think of it not as a movie waiting to be played, but as every single frame of that movie laid out on a table at once with no order to them. There is no past, present, or future, only a vast and timeless now. So how do we get from that frozen landscape to the flowing river of time we all experience? The key might lie in a quantum process called decoherence. This is what happens when a quantum system, which can be in many states at once, interacts with its environment and is forced to pick a single, definite state. In this timeless quantum realm, the universe was in a superposition of all possible states, but through a process we do not yet fully understand, perhaps through its own internal correlations or a kind of self-observation, it underwent a cosmic decoherence. This is the moment the timeless potential collapsed into a specific sequence of events, creating the consistent history we call causality. Time, in this view, is not a fundamental feature of reality but an emergent property, a story that the universe tells itself. The Wheeler-DeWitt Equation is not just a mathematical curiosity, it is a profound symbol of our struggle to understand existence itself, pointing toward a pre-temporal state that is not a void, but a realm of pure, unmoving quantum possibility. This vision of primordial information finds a stunning home in the geometry of higher dimensions. Brane cosmology proposes that our entire universe is not an island in emptiness, but a three-dimensional membrane or brane, floating within a much larger, higher-dimensional reality known as the bulk. Before our clock started ticking, this brane and others like it might have been drifting in this timeless hyperspace, vast sheets of potential reality moving or vibrating in a silent, eternal dance. Their motion was not through time as we know it, but through extra-spatial dimensions we cannot perceive, a form of existence utterly alien to our own. The energy for our entire cosmic genesis could have come from a cataclysmic collision between two of these branes. Imagine two immense, silent sheets of glass in a dark void, drawn together by an unseen force. Their impact would not be a simple crash, but a release of extraordinary energy across their entire surfaces, a fiery awakening that flooded each brane with the raw material of a new universe. What we call the Big Bang from this perspective was not an explosion from a point, but the moment our specific brane was struck into being, a shockwave of creation rippling across a membrane of reality. This framework transforms our cosmic story into a single episode in a grander, multidimensional drama. The silent state before our time was not a void, but a bustling, higher-dimensional arena where the laws of physics allow for countless universes to be born from the interactions of these colossal structures. Our existence is not special, it is simply local, a single reality playing out on our three-dimensional slice of a much richer, hidden cosmos. These competing ideas of quantum foam and colliding branes seem worlds apart, yet they are both attempts to answer the same profound question using the incomplete tools we have. The true frontier lies in finding a single theory that can weave them together, a unified description of reality that works for the immense gravity of a black hole and the spooky weirdness of the quantum world. This quest for a theory of quantum gravity is our greatest scientific challenge, and it is within these efforts that we find the most mathematically rigorous visions of pre-existence. The goal is to eliminate the singularity, that point of infinite density where all our equations break down. In its place, theories like loop quantum cosmology propose a smooth transition, a cosmic bounce where time itself transforms. Imagine the moment of the Big Bang not as a violent explosion from nothing, but as a gentle turning point, like a ball rolling smoothly up one side of a valley and down the other. There is no sharp edge, no impossible infinity, just a seamless geometric shift from a previous state of contraction into our current expansion. Time, in this view, did not begin but was reborn. Other approaches, like those in string theory, use a different mathematical toolkit to achieve a similar result. They describe the entire history of the universe, including its pre-temporal phase, with a timeless wave function. This is not a wave of water or sound, but a wave of probability, a mathematical object that encapsulates all possible states of the universe at once. Before our arrow of time emerged, the universe would have existed in a superposition of all these potential states, a silent, frozen landscape of what could be. The Big Bang, then, was the moment this wave function collapsed or evolved, selecting one specific, consistent history from the infinite possibilities. It was the universe choosing a path, a story to tell, and in doing so, creating the flow of time as the narrative of that story unfolded. These theories are immensely complex, their mathematics stretching the limits of human comprehension, but their promise is simple and profound. They aim to replace the terrifying nothingness of a singularity with a something we can describe, a quantum gravitational phase that operated by its own consistent, if alien, rules. They paint pre-existence not as a void, but as a domain of pure geometry and potential, a state that smoothly and inevitably gave way to the dynamic, temporal cosmos we inhabit. While we lack the technology to directly test these ideas, they represent the pinnacle of our intellectual journey to understand our own origins, proving that even the most fundamental questions about time and existence are not beyond the reach of scientific inquiry. Such a state of perfect symmetry would be a reality of profound simplicity and unity. Every force, every particle would be identical, governed by a single, elegant mathematical principle. There would be no distinction between matter and energy, no separation between the forces that bind atoms and those that guide the stars. This primordial state would be the ultimate order, a cosmic blank slate where nothing happens because there is no difference, no gradient to drive any change. It is a form of existence so uniform it borders on non-existence, a silent, frozen perfection. Then something shifted. In a process known as spontaneous symmetry breaking, this perfect balance became unstable. Think of a pencil perfectly balanced on its tip. It represents a state of high symmetry, but it is also profoundly unstable. The slightest breath of air, the tiniest quantum fluctuation, will cause it to fall, choosing one specific direction over all others. Its symmetry is broken, but in doing so, it creates a new, richer reality defined by up and down. The Big Bang may have been the universe's pencil falling. As this perfect symmetry fractured, the single unified force splintered into the four distinct forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. The uniform energy field condensed into the diverse families of particles that make up everything we see, from the quarks in an atom to the photons in a beam of light. The incredible diversity of our cosmos, from swirling galaxies to the chemistry of life, is not a sign of initial chaos, but the direct result of this great breaking. The asymmetry we live with is the very reason anything complex can exist at all. This means the silent era before time was not a barren void, but a state of immense potential, a perfect symmetry holding within it the blueprint for every galaxy, star, and living thing that would ever be. Science and theology have often been portrayed as adversaries, but their questions about pre-existence echo one another in profound ways. theologians across countless traditions have grappled with the concept of a state before creation, frequently arriving at a similar conclusion, that ultimate reality exists in a divine realm outside of time itself. In this view, God or a primordial consciousness is not a being within the universe, but the very ground of being itself, the uncaused cause that exists eternally without beginning or end. This framework sidesteps the scientific puzzle of a first cause by placing the origin of everything in a dimension that transcends the physical laws it created. The moment of the Big Bang, then, is not seen as the absolute beginning, but as the instant when a timeless will initiated the temporal order, the point when the eternal consciously entered the realm of time and space. This is not merely an ancient idea. Modern philosophical theology explores concepts like a block universe, where God perceives all of time from creation to consummation in a single, eternal now. This mirrors the frozen cosmos of the Wheeler-DeWitt Equation, but adds a conscious observer to the static picture. The dialogue between these fields is not about one proving the other wrong, but about recognizing the different languages they use to describe the same profound mystery. Science maps the mechanics of how something could emerge from a quantum vacuum, while theology ponders the why, the possibility of a purpose or a mind behind the mathematics. This conversation enriches our understanding, suggesting that pre-existence might not be a barren void to be explained away, but a reality encompassing dimensions of existence we are only beginning to glimpse, whether they are called spiritual, metaphysical, or transcendental. These profound questions are no longer confined to pure theory. The next great leap in understanding pre-existence will come from experiments that push the very limits of technology. Our most powerful telescope is not in space but buried deep within the fabric of spacetime itself. We are on the cusp of directly detecting primordial gravitational waves, the faint ripples left over from the universe's violent birth. These waves are a snapshot from the first fraction of a second, a whisper from a time before the first stars, carrying imprints of the processes that created everything. If we can capture their unique pattern, it could tell us if the universe began with a bang, a bounce, or a collision of cosmic membranes. Other experiments are delving into the quantum nature of gravity itself. By studying the behavior of particles at incredible energies or in extreme states, we might find tiny deviations from Einstein's predictions, subtle cracks in the smooth fabric of spacetime that hint at the grainy quantum foam that lies beneath. We are building machines to probe reality at the Planck scale, searching for the fundamental pixels that make up our universe. These are not just tests of physics, they are time machines, allowing us to peer backward through the veil of the Big Bang and glimpse the conditions that made our reality possible. The answers we seek are not written in the stars, but encoded in the most fundamental vibrations of existence, waiting for us to learn how to listen. Our journey through these breathtaking possibilities reveals a cosmos far stranger and more magnificent than we ever imagined. We have ventured from the seething quantum foam to the silent clash of cosmic brains, from the timeless equations of a block universe to the idea that reality itself might be a grand computation. Each theory, whether it speaks of a cyclic universe or a holographic projection, challenges our most basic intuitions about beginnings and endings. They teach us that time itself may not be the fundamental ruler we perceive it to be, but an emergent property, a story that the universe tells itself. While we may never possess a single, definitive answer to what came before, the pursuit itself transforms us. It deepens our awe for the profound mystery we are all a part of and celebrates the human spirit's relentless drive to question. These ideas are not conclusions but invitations to think bigger, to wonder more deeply, and to always look beyond the horizon of the known. If this voyage into the unknown has sparked your curiosity, share your own thoughts and questions in the comments below. Be sure to subscribe for more journeys to the edge of understanding. Until next time, keep looking up and wondering what lies beyond.